I'm going to talk today about joint work with Matthew Wright, who's a visiting professor at St. Olaf. This is work about a generalization of persistent homology called multidimensional persistence. Now, persistent homology is one of the central tools in topological data analysis. It provides invariants of data called barcodes, and a barcode is just a collection of intervals on the real line. So, for example, a barcode might look like this, where we just stack the intervals in the barcode vertically. And these barcodes have been used extensively in applications in the last 15 years or so. And in particular, they've been used.
How do you decide to organize vertically?
So it somehow, well, in this picture, they've been ordered longest to shortest, top to bottom. But people do it different ways. But the important thing is that this is a collection of intervals on the real line, and there are different ways to represent it.
Is there a thing on the left, or is it just dirt on the screen?
Yeah. Okay. So, yeah, there really is something on the left. It's not. Okay. Yeah. So first of all, since, yeah, I stole Uli's figure. Uli's here, and I put it up here. He shouldn't be blamed for the bad scaling of this, but this is a point cloud data set living in R2. And this is its associated first barcode. There's actually a barcode for each non-negative integer I for this data set. Okay, so in any case, these barcodes are used for different things, including defining features for machine learning. But one of the central applications, since people started worrying about persistent homology about 15 years ago, has been for exploratory data analysis and visualization, trying to use persistent homology to understand something about the coarse scale global geometric features in our data. And there are a number of practical tools available for computing persistent homology now, software that you can download off the internet and start using right away. So what is multidimensional persistent homology? Well, as the name suggests, this is a multi-parameter generalization. Now, ordinary persistent homology associates to data a filtered family of topological spaces, a filtration, one parameter growing family, and it uses this topological object to define the barcode by employing standard topological and algebraic methods. And so in multidimensional persistent homology, we associate to our data a multi-parameter family of topological spaces. For example, a guy like this over here that I've drawn is a two-parameter family of topological spaces. And I'll tell you later on, right? So intuitively, it's essentially a grid of topological spaces, right? So I think of this guy as the topological space at parameter 1, 1, say. This guy as a topological space at parameter 2, 1. This guy as a topological space at parameter 1, 2, and so on. Okay? Now, I'll go into all of this in detail later, but this is just to give you a sense. Okay, so in multidimensional persistent homology, we're going to begin by associating to data these two-parameter families of topological spaces. And it turns out that multidimensional persistent homology, these two-parameter families, arise naturally in applications, and especially in the study of noisy point cloud data. But in contrast to the 1D case, there are no practical tools yet available for multidimensional persistent homology. And so our work seeks to address this gap in the special case of two-dimensional persistence. So in this work, we're introducing a practical tool for the interactive visualization of two-dimensional persistent homology. And Matthew and I have been working on this tool for about 2 years, and it's not yet publicly available, but in some sense, it's essentially done. And we're getting it ready in terms of polish and deployment stuff. And so there'll be a paper on this appearing, I think, in the next couple of weeks. So this is what the interface for our tool looks like. You can see that there's a lot going on.
So
and
you're expecting to release the software to the public in a few months?
Oh yeah, that should have said 2000, or I mean early 2016. Yeah, winter 2016. So, yeah, that's a typo. Thanks. Yeah, it'll be free. Yes. No, it'll be open source. Okay, so, all right. So now, okay, so this talk is going to be about making sense of this picture here. But I just want to sort of just give you guys a flavor of what this thing is. I want to show you quickly what the tool looks like. And this is what you saw before. And so the key feature of this tool is here we have, we think of, this thing isn't fitting on the screen so well. I may have to fuss with this resolution. 1 second, please. Or actually, perhaps the quicker thing to do is just resize this on the fly. How about now? All right, that'll do. Good. Okay. So, right. So here are our two parameters corresponding to our two-dimensional filtered object, and what our tool does is allows us to choose a one-dimensional slice of this two-parameter space. Of this 2D parameter space, and it turns out we'll see that for each one-dimensional slice, we're going to have an associated barcode, one of these collections of intervals, and we just plot the barcode like so, parallel to the line that we've selected. And the main idea of the tool is to allow you to browse these guys interactively in real time, like I'm doing here. All right, these full two-dimensional persistence objects are very algebraically complicated objects, so we'll see, there's no good direct notion of barcode for these guys. So we're doing a few of the next best things that we can do, and one of them is to probe these 1D slices interactively. Okay, so there's a lot of stuff that should be unclear now, like what is this gray stuff? What are these red dots and green dots and yellow dots? And I'll explain all of that to you. But I just wanted to show you what the thing is, and I think for...
You say there's not a good way. I mean, is that like an intuition or like a formal statement?
People are laughing, but it's a very good question. It's a fair question. So, yeah. So
if you just apply the sheaf formalism that goes into the one-dimensional thing, what do you get? That would be an intrinsic.
All right. So the answer is that there's a. I'm kind of skipping ahead now, but under reasonable finiteness assumptions, you have a Kroll-Schmidt theorem for the algebraic objects that come out. So you do have a essentially unique decomposition of your objects into indecomposables, but those indecomposables can be way more complicated than in the 1D case. Okay, so they're not going to be parameterized by intervals or some 2D analog of intervals in particular. Okay, and yeah, maybe I won't say that, but I'll explain that in a more accessible way soon. All right, so okay, a lot of this talk is going to be about introducing persistent homology basics. So I just thought I'd explain what we're doing mathematically in this project right away before I delve into background material. So on the mathematical side, the main contribution is a theoretical and algorithmic framework for performing efficient queries of these barcodes of 1D slices of 2D persistence objects so that we can browse these guys in real time. And also as a part of that, we need to compute bigraded Betti numbers, which are certain standard invariants of these 2D persistence objects. And we introduce a fast algorithm for this that runs in time O of n cubed, where n is some measure of the size of the input. And also, and this is still a story that's developing, but as part of this project, we've had to devise some novel algorithms for computing one-parameter families of barcodes. And there are ideas for this out there. There's the Vineyards persistence updates of Dmitry Morozov and his co-authors, but for some things, they don't do as well as you want to. So we've had to worry about this. And well, I I thought this might be of interest to some of the dynamical systems crowd, because I know a lot of people are computing one-parameter families of barcodes and trying to understand dynamics of that through the persistent homology lens. Okay, so with that said, I'm going to introduce multidimensional persistent homology. Actually, I'm going to start with 1D persistence. I'm going to explain our tool in some detail, and then if time does permit, then I'll discuss these theoretical and algorithmic underpinnings just a bit. Okay, so let's talk about 1D persistence. So as I told you, persistent homology associates barcodes to data, and here's the picture with the small point cloud data circle on it again. So what do we mean by data when we say that persistent homology associates barcodes to data? Well, typically we mean one of two things. Either we mean data is a finite metric space, which may or may not be embedded into a nice space like a Euclidean space. We also call this point cloud data in our world. Or my data set might be a function. It might be a function from some arbitrary topological space, say Rn, to R. And usually we ask that the domain be R, although we don't always ask for that. And so yes, as I said, these barcodes are collections of intervals, and the way that we want to interpret them is like this. We want to think of each interval as corresponding to a topological feature of our data, and we're going to think of the length of the interval as some measure of the robustness of that feature. Okay, so I drew a variant of this example up over here on the board precisely because I thought that point cloud data circle was sitting a little small. So for example, if I have this guy over here, its first persistence barcode might look like this, and this single long interval here would bear witness to the fact that there's some sort of discretized cycle in this data. Okay, so one remark further about these barcodes, about an alternate way of representing them. In practice, and in particular in any computational setting, our barcodes are going to be of the form BD, left closed, right open, and then all the information in the interval is in B and D, and we can just regard the barcode as a collection of points BD in the plane with B less than D. So I could have the interval stacked like this. Now I've done it vertically, and then alternatively I can display this as this diagram like that, collection of points. And D, I'm lying a little bit because we're also allowed to have D be infinity. But okay, so that's the persistence diagram representation. Good. So how do we construct these barcodes? Well, there's a standard pipeline for this, and it proceeds in 3 easy steps as follows. We begin with our data, and we associate to this data a filtration, this topological object, and via an application of homology, we map this filtration to an algebraic object called a persistence module. And then it turns out that we have a nice, clean structure theorem for these persistence modules that realizes the barcode as a combinatorial invariant of these guys. In fact, a complete combinatorial invariant in the sense that it describes the persistence module completely up to isomorphism. And I'm going to walk you through all of these steps now in more detail. First, I'm going to define for you precisely what a filtration and a persistence module are. So a filtration is a simple object. It's just a collection of topological spaces Fa indexed by the reals or alternatively by the integers, such that A is less than or equal to B. Okay, so in the z-index case, this is a particularly simple intuitive object. This is just a diagram of spaces of this shape. So I have F0 sitting inside of F1, sitting inside of F2 forever, and also forever backwards like this. Okay, so now let's talk about persistence modules. And I'm going to first fix a field K, any field, and then I'm going to define a persistence module M to be a collection of K vector spaces MA, again indexed either by the reals or by the integers together with commuting linear maps MAB from MA to MB whenever A is less than B. And so this is just a diagram of the same shape, except it's a diagram of vector spaces and not topological spaces. So again, it'll look like this in the Z index case. Okay, so now we know what all of these objects are. And we need to talk about these red arrows. How do we pass from data to a filtration and so on? Okay, so, well, let me say first of all that the way this pipeline works in the standard setup is always essentially the same from here on down. This is turning a standard crank. And we do this step in different ways depending on the setting. I'm going to talk about probably the most standard way that we see in applications in the case that our data is a finite metric space. This is the RIPS filtration construction. So for P of metric space and A, a real number, I'm going to define a simplicial complex RIPS PA as follows. First, I'm going to take the vertex set of the simplicial complex just to be the underlying set of my metric space, P. And then I'm going to define the one skeleton of the simplicial complex by saying that RIPS PA contains an edge QR if and only if the distance in this metric between Q and R is less than or equal to A over 2. Okay, so for example, here's one of these guys. Here's my set P in blue. And then if 2 points are close enough, I connect them by an edge. And the threshold for that is given by A over 2. And then finally, this specifies the one skeleton of my simplicial complex. And I just take RIPS PA to be the click complex on this one skeleton. And that essentially means that I add in every higher simplex that I possibly can to the complex. So for example, if I have 3 vertices and they're all pairwise connected by an edge, then I add in that triangle, and so on. Okay, well, so if I increase A, then I allow myself to connect more edges, and my one skeleton grows, so my click complex grows, and this tells me that the collection of all these guys, RIPS PA, as A ranges over the reals, gives me a well-defined filtration. It gives me this growing family of simplicial complexes. Okay, and this is how, in this persistence world, this is the most common way of going from the discrete data set with a notion of distance to some continuous object where it can start to apply methods designed for continuous objects, like homology. So, in particular, so now we've gone from a data set to a filtration, and we want to pass to a persistence module. So what we're going to do is, as I said, we're going to apply homology with coefficients in the field K. Homology with coefficients in the field K associates to each topological space, a K vector space, and each continuous map of topological spaces, a linear map between K vector spaces. So applying homology with coefficients in the field to each space, each topological space, and each linear map, each inclusion map in the filtration, rather, gives me a persistence module, this diagram of vector spaces. And that's how we pass to the algebraic world. Now finally, we need to talk about obtaining the barcodes from these persistence modules via a structure theorem. And there are different variants of this structure theorem. I'm going to describe one in the Z index case. And by the way, all of these are essentially graded variants of the fundamental theorem for finitely generated modules over a PID. Right, so they're similar to things that you've seen before if you take math classes or ever have. So okay, so here's how this goes. So what I need to do before I give the theorem is define certain kinds of special simple modules called interval modules. And these are, very simple indecomposable guys. And the way I do this is I say, first of all, for A less than B, an integer, I call the interval AB, left closed, right open, a discrete interval. And then I define the interval module IAB corresponding to this discrete interval as follows. So this is going to be a module whose vector spaces are all 0 or copies of the field K. And I need to tell you where these copies are. Well, the first copy of the field K is going to live at index A. The last copy of the field k is going to live at index b minus 1. And in between these guys, I'm going to have copies of the field k everywhere and identity maps connecting them. And that's this interval module, this nice friendly guy. And for a clean version of this theorem, we also want to talk about infinite analogs of this guy where the k's can go on forever in either direction. So I define infinite discrete intervals and their corresponding interval modules in a similar way. Okay, so the theorem will now be stated in terms of these guys. It says, for M, a z-index persistence module with finite dimensional vector spaces, there exists a unique collection of discrete intervals, Bm, such that M is the direct sum of the interval modules corresponding to the discrete intervals in this collection. Okay, now I'll confess that I haven't defined direct sum in this world yet, and I'd rather not do it. But for those of you that don't already know what I mean, it's the sort of obvious way of assembling two persistence modules into a larger third. Okay, so now, all right, so this collection of intervals is unique. So it's an invariant of the module, and we call this guy Bm the barcode of M. So that's how we get these barcodes from data in those steps. And so after all that, we get a nice guy like this from a data set. Good. All right, so what is there to say about this? Well, I told you already that these guys are computable. And in addition, they have a nice property that people like to fuss over in this community. And that property is that these barcodes are stable. So persistent homology, this can be formulated in different ways, including in very general algebraic ways. But let's talk about stability for point cloud data. The result says that the persistent homology of point cloud data is stable with respect to the Gromov-Hausdorff distance on finite metric spaces. Okay, and to really make that precise, I need to define Gromov-Hausdorff distance, and I need to define what my metric is on barcodes, and I don't want to do that today. But informally, I'll at least tell you what a bound on the Gromov-Hausdorff distance tells us about our point cloud data. So if I have a data set like this, and say I perturb some of the points, perturb the distances between points, and perhaps remove points that are close to other points, perhaps add in a point near another point. So say I go from this data set to something like that, right? They have different numbers of points, but somehow they're close in this sense. Then their barcodes are going to be similar. And that's a useful fact to us. This is applied mathematics. We want to be able to use these kinds of tools to study noisy scientific data. And so data is always going to have some kind of measurement error. So it's good that we have this kind of property. But there are limits to this stability for persistent homology. And in particular, persistent homology is not stable with respect to outliers. Right? So if we have our favorite TDA example of the circle, and we might have this associated barcode that looks like this with this long interval. I should have put this figure up right at the beginning of my slides because it's a good figure, but I didn't think of that till now. Anyway, so we have this nice long bar that bears witness to this big cycle over here. If I add in just a few low density outliers into my data set, then the barcode can change drastically. In fact, it can even change drastically with the addition of 1 point. So in particular, if you look at the barcode here, this long interval is gone now. And that's a problem because the story for TDA that we want to tell is that we'll be able to look at these long bars and they'll be representative of significant features. But there's this robustness problem.
The circle becomes null homologous because you add a bunch of triangles to cover the disk.
Yes. Yeah, as I build this RIPS complex, this hole will now quickly fill up at small scales. And so it's getting topologically cut off. Okay, so this is a problem, so we want to correct for this problem somehow. And there are different ways that have been proposed to do this, but they all, in some sense, lead to the same considerations. In particular, they lead us to the study of multidimensional persistence. So let me shift gears now and start talking about multidimensional persistent homology. Okay. So if we want to develop multidimensional persistent homology, then we're going to need an analog of our pipeline for 1D persistence in this 2D setting. How's that going to look? Well, first we're going to associate to our data this 2-parameter family of spaces called a bifiltration, which we touched on at the beginning of the talk. Just like before, we'll have an associated algebraic object called a 2D persistence module. And now, okay, just like before, we'd like to be able to get a barcode out of this guy, and some kind of 2-dimensional barcode. But as we already discussed briefly, there's some problems with this, and so we'll talk about what to do there. All right, so first let's define these objects that appear in this pipeline, the bifiltration and the 2D persistence module. To define the bifiltration, I need to first define a partial order on R2, and I do this by taking A1, A2 to be less than or equal to B1, B2, if and only if A1 is less than or equal to B1 and A2 is less than or equal to B2. And just to
Are there ever any cases where you might want a lexicographic order, like compare compare the ones that show up first and then the ones that come after, like the dictionary?
Good question. Yeah, I don't know. I can imagine cases, at least for theoretical things, where you might want to have 2 copies of R, but as a set, R times R squared. No, I don't know. Lift this board? Yeah, sure. Of course, I don't know what writes that. Good. So, okay, I just want to make clear what this partial order looks like geometrically. The risk of being pedantic. So A is going to be less than or equal to B if and only if A lives in the lower left quadrant with corner B. Okay, so then a bifiltration is a collection of topological spaces, either indexed by R2 or by Z2, such that the space at index A sits inside of the space at index B whenever A is less than or equal to B. So if you look at this picture, right, here's my 2-parameter family. This is part of a filtration indexed by Z now. If I move to the right, my spaces get bigger, or at least they don't get smaller. And if I move up, the same is true. So this is a well-defined bifiltration. Okay, and actually somehow these conditions that I have these inclusions theoretically aren't so important. They're useful for computational things sometimes. But anyway, the convention is to require that. Now similarly, a 2-dimensional persistence module M is a collection of k vector spaces MA, indexed again by either R2 or Z2, together with commuting linear maps MAB. And these go from MA to MB whenever A is less than B. So in the Z index case, this amounts to the data of a commutative diagram of vector spaces and linear maps of this grid shape. So every square is required to commute. Okay, these are my objects. And as before, if I apply ith homology to every space and every map in my bifiltration, I get a 2D persistence module. So good. Now to flesh out our discussion of 2D persistent 2D persistent homology, I need to talk about 2 things. First, how do I go from data to a bifiltration? And secondly, this part, barcodes of 2D persistence modules. So let's deal with the first question first, in the case again of point cloud data. Now, to provide some context for what I'm about to explain, let me just talk about what people have done to deal with this kind of problem in the past. So there's some work on application of persistent homology to the study of natural scene statistics by Carlson and co-authors from, I guess it was published in 2008. And in this work, the authors dealt with a situation much like this, where they had interesting structure at high interesting structure in the high density subsets of their data, and somehow that was being corrupted by low density noise, like we have in this second frame here. And so I think the most obvious first thing to try to do in this case is somehow cook your data so that you get rid of the low density stuff, to clean it so that your picture looks like this. And this is exactly what these guys did in their paper. They somehow thresholded out the low density stuff to clean things up. And so in some sense that's reasonable, but it's also, it also has some problems. First, what are the problems? So first, this kind of thresholding requires a choice of scale, and your results, when you pass down to the level of persistent homology, might be unstable with respect to that choice of scale. Also, sometimes your data has interesting structure simultaneously at several different levels of density. And so, much in the same way that when we play these persistent homology games, we don't fix a single scale parameter for our RIPS complex, and it's natural to ask to persist over some kind of density threshold. And so the construction that I'm going to explain to you next is proposed by Carlson and Zomerodian in 2006, I believe, and it sort of gives the inevitable multidimensional, the inevitable bifiltration that comes out of these considerations. So for P, a finite metric space, first I'm going to let gamma from P to R be a codensity function on P. And what do I mean by that? When I say codensity function, I mean just that gamma is high at outliers and low at dense points. And there are different ways of making this precise. Here's one that was used in this earlier work that I described a moment ago. They fix a non-negative integer k, some bandwidth parameter, and they let gamma of x, for x a point in the metric space P, be the distance to the kth nearest neighbor of x in P. All right, so maybe it's good to draw a picture to illustrate this. Can you guys see on the boards, by the way? It's just the lighting is low, but okay, good. So for example, let's say I have a really densely sampled circle point cloud like this, and I have an outlier over here, and I say k is equal to 5. So I look over here at, let me draw some more points. Okay, I look over here and I say, what's the distance to the 5th nearest neighbor? I don't know, that's probably this distance, right? And because this is densely sampled, that distance is small, so the function value will be low. Whereas if I look at this point over here, then the 5th nearest neighbor maybe is this guy. That's a much longer distance, and somehow that measures the fact that this guy is an outlier relative to this choice of k. All right, so anyway, we choose some function with this property, and now I'm just formalizing this notion of thresholding the data. For a real number, I define the a sublevel set of gamma, which we denote like this, gamma sub a, to be the set of all points y in P such that gamma of y is less than or equal to a. That's it. It's sort of exactly what you think it should be. And that's how I go from a guy like this to a cleaned up guy like that, at least for suitable choice of a. Okay, and so now finally, to define a bifiltration for a, b, and R2, I let f sub a, b denote the RIPS complex on gamma of a, this cleaned up data set with scale parameter b. And so as a grows larger or b grows larger, these objects grow bigger. And so the collection of all of these together with inclusion maps is the bifiltration, as I want. Okay, so this is a way of playing these RIPS filtration construction games in a way that's density sensitive somehow, also in a multi-scale fashion with respect to density. So a couple of remarks about this. So first, I don't need to use, to carry out this construction, I don't need to use density. I could use all kinds of different functions here in place of density, and people have proposed different choices. And different choices of this function will topologically capture different aspects of the geometric structure of my data that I might be interested in. And secondly, and perhaps more interestingly, there's something uncomfortable over here, which is, it's uncomfortable to me anyway, it's this choice of k, right? So we'd really like to be able to build parameter-free invariants of data, right? We're building these complicated invariants, and in exchange, it'd be nice if they were genuinely parameter-free. And there's a way to vary this construction that will avoid the choice of this scale parameter. And I'll be happy to tell you about it later. So anyway, that awkwardness can be dealt with, is my point. So good. All right, so now we're on to the fun part. We know how to go from data to a bifiltration. Homology gives us the 2D persistence module. And now we want to talk about this problem of defining the 2D barcode. What can and can't be done, and what do we do? So now, anytime you talk to somebody sensible about these kinds of things and tell them about 2D persistent homology, the first thing they'll ask you, well, they won't ask you it if they have a lot of algebraic background, but otherwise they'll ask you, can't we define the barcode of a 2D persistence module as some collection of nice regions in R2? Well, the barcode is a collection of nice regions in R1, and this is the 2D case, so why shouldn't things be like that? But the short answer to that question is no, and the slightly longer and slightly more correct answer is you can't do it without making some significant compromises. So you're not going to be able to do it in the way that you want, in short. And yeah, we could make that precise if we wanted. But here's the underlying algebraic story. And I'm repeating myself now from the beginning of the talk. So we have a Kroll-Schmidt theorem for these 2D persistence modules, at least under some mild assumptions, which are always satisfied in the computational setting. And this tells us that for any module M satisfying these assumptions, there exists a collection of indecomposables M1 through Mk, unique up to isomorphism and, of course, up to reordering of these guys, such that M is the direct sum of these indecomposables. So this is good, I think. This tells us that just like in the 1D case, there's some unique collection of, essentially unique collection of building blocks out of which I can build my persistence module M. But now we come to the difference between the 1D case and the 2D case. And the difference is that unlike in the 1D case where my indecomposables were parameterized by intervals, somehow that's like a 2-parameter family of objects, like 4 sets of 2-parameter objects. In this case, the set of possible isomorphism classes of the indecomposables is extremely complicated. And this is a lesson from standard results in quiver theory. So quiver theory worries about these kinds of questions, like how nasty can the collection of isomorphism classes of indecomposables of the diagram of vector spaces be? Is the collection of indecomposables computable? Yes, I believe that it is. I don't know this aspect of the subject too well, but
I mean, the whole set is not computable, but up to some bound of total dimension or something like that.
So I interpreted your question as, is this decomposition computable? Right? That's the question? So in any case, there are some polynomial time algorithms for this. For instance, it seems that there's an n to the 6th algorithm where n is some measure of the complexity of your input. Okay, so for example, it's known that the set of possible isomorphism classes of diagrams of vector spaces of this shape can be quite nasty. And so it turns out you can use this fact to check that the set of possible isomorphism classes of indecomposable persistence modules in 2D is at least as nasty. All right. And so this tells us, well, so in principle we could define the barcode as the collection of isomorphism classes of indecomposables, but that's going to be a nasty object. It's going to be hard to visualize directly on a computer screen in any way that doesn't, well, you could do it, but you'd probably have to throw away a lot of information to do it in a reasonable fashion.
Somebody, did you explain where the 2D helps you solve the outlier problem?
Yes.
You did explain that?
Yeah. Yeah, so that was this slide here, right? That's how we construct this RIPS by filtration. And at different scales, we remove outliers. Exactly. Yes. Okay. All right, so anyway, so let me move on then. The point here is that, okay, so what you might hope to be true isn't true, but nevertheless, we certainly can define useful invariants of multidimensional persistence modules, and I want to suggest 3 of them to you now. Okay, so I'm going to talk about 3 that our tool visualizes in specific. So first, we visualize, this is a very simple one, we visualize the dimension of the vector space at each index. As I mentioned, we visualize the barcodes of one-dimensional affine slices of my 2-dimensional persistence module. And then third, this is the green and the red dots, we visualize multigraded Betti numbers of the persistence module. So let's talk about these now. So dimension of the vector space at each index is self-explanatory. We visualize it in grayscale. So where the dimension is 0, we take the region to be white, and the darker the region is, the larger the dimension is. That's our convention. And you can compute this easily. In fact, we need to do it as a primitive for the other things that we do anyway. And I like this. I think it's intuitive and it's simple. I can learn something from it right away, but it has its limitations. It's not stable, first of all, in the usual senses. And secondly, it tells us nothing about persistent features in the data. Right? It could be that somehow what we care about in this world, just the way we care about the long bars, this is about features in my persistence module that are alive here algebraically and live on to over here in the sense that the rank from here to there is non-zero. So similarly, we care about features that are alive here and live on up to here in the image. And this picture will tell me, is not guaranteed to tell me anything about that. Okay? So to address that, we work with this one-dimensional slice methodology, which is complementary in a sense. So we let L be an affine line in R2 with non-negative slope. And I'm just going to formalize this stuff that I showed you before now. Well, the restriction of M to the line L is a one-dimensional persistence module, ML, in the sense that, well, you can think of this guy as parameterized by the real line. At every point here, I have a vector space, and for any pair of points, I have a map forward from the one vector space to the other. So I have a full-fledged persistence module. And so
Are you doing some sort of a band? Because if you get an irrational slope, there's no vertices, and then so you're hopping from one place where you have small, close vertices, and then nothing, and then large vertices, and then nothing. And then
sorry, I didn't understand that
change
question.
The slope of your line.
Uh-huh.
And that kind of a problem. Is that
Yeah.
doing a band or something, or what?
So I'm not sure what a band is, but we simply are selecting, I mean, based on the user input, we're selecting some choice of slope, and we do this quickly, of course. And there's no irrational numbers involved, right?
But you're sliding the blue lines around, right?
Yeah,
So the slopes can be irrational.
I guess so, but we...
Slopes can miss all of the vertex points in the picture.
The vertex points are at every pair of real numbers. They've completed it. They've made it continuous.
Yeah, but the transitions are happening.
The 2 parameters, scale and density.
yeah, they could be. I mean, we're talking about an abstract algebraic. We're talking about working with these 2D persistence modules abstractly. Okay, so for what I'm saying to make sense, I don't necessarily. I mean, yeah,
But in your example, those were the 2 parameters.
Yes, exactly. But this would make sense for any one of these objects, right? These, 2-parameter families of vector spaces and linear maps. I showed you the Z2 indexed ones because that's what I can draw on a slide. That's what I can visualize. And these R2 indexed ones are these kind of continuously indexed variants. So I have a vector space at every point. Okay, good. All right, so I have this restricted persistence module, and so therefore ML has a barcode. Call it B of ML, and this is, I just can think of this as a set of intervals in L, and I just draw these offset from the line like you saw. All right. Okay, and an important, sort of simple but important fact is that these barcodes are stable in two senses. The first sense is that they're stable with respect to perturbations of my line. So if I move my line, then the barcode is going to change continuously in some sense, and you saw that already. And the second sense is that they're stable with respect to perturbations of my module. And there's good language available for talking about what that means. And so my module changes a little bit, then these barcodes aren't going to change too much. And so maybe I'll mention that stability depends on the slope of the line. So as long as the line is not horizontal or vertical, I have that stability, and somehow the more diagonal the line is, the stronger that stability is. And that suggests that in this exploratory data analysis methodology that we're trying to sell, diagonal lines should play an important role. Okay, so now
If I choose your distance and your density, right?
uh-huh.
But if I rescale density, by changing what you said before, just rescale my label, right?
Yeah, I understand what you're saying.
I've changed my slope.
Yes, yeah, that's fair enough. No, so the stability, so I would, for this, what I would call external stability with respect to change in the module, this is gonna be true with respect to, for example, the interleaving distance, right? So if the modules are epsilon interleaved, that's some notion of them being close, then that's going to control the distance between the barcodes. You're going to have some Lipschitz stability, but that stability will depend on how this line is sloped. But under your rescaling, your interleaving object becomes this this isotropic, this asymmetric interleaving object, and so it would make sense here, but okay. All right, so finally, multigraded Betti numbers, and I might not say too much about these. But these are what correspond to these green and red and yellow points here. I'll say this: for m an n-dimensional persistence module and I, any integer between 0 and n, we can define functions xi sub I of m. This is a function from Rn to the non-negative integers, and we define them. So we can define them in terms of homological algebra, and the definition is xi I of m at index A is the dimension of the vector space in the ith Tor module of m and k at index A. Right. So that's, for me, that's kind of a mouthful for several reasons. So first, what do I mean when I say k is a module? I said k was a field, so just to be clear, if this is index 0, 0, this is the module where I have k at index 0, and 0 is everywhere else. I don't want to draw them, but k at index 0, 0, that's the only non-zero entry. Okay, and that also makes sense in the R index setting. But, okay, so let's forget the homological algebra definition and just talk about them intuitively. Intuitively, xi0 of m is, I'll say, the dimension of what is born at A. So for example, if you look in this picture, the dimension of everything is 0, but over here I have a green dot. Something is being born because you see non-trivial vector spaces afterwards. And similarly, over here, let's look at this red dot over here. You have these two births here, and they're creating one-dimensional vector spaces, I claim. But over here, afterwards, I still have one-dimensional vector spaces, and that's because somehow these algebraic features are colliding up here. So that red dot is witness to that. In any case, this is a standard invariant that people think about. it can be defined in a local and maybe more intuitive way using causal homology. And I'm going to skip that in the interest of time. And I'm going to come now back to my tool and show you, well, a variant of the first example that I showed you. And now that we understand a bit more, let's look at it again. So I'm going to consider a code-density RIPS-by filtration on a noisy point cloud data circle, like we've been talking about. And in this example, it's a small example. It's 240 points with about 200,000 simplices. We certainly can do bigger than that, but this is what I'm going to show you. So to make our computation easier, I'm going to round the distances in the code densities in this filtration to lie on a 30 by 30 grid. And I'm going to consider the visualization of the first persistent homology. And morally, right, we have this cycle here. We hope that we can recover that. And so I did this computation on the way over here when I was on the train, so it didn't take too long. And so here's what we saw again before. And let's see what's happening. This is the part where I show off the little bells and whistles of the tool. So we can remove the first and second multigraded Betti numbers and just see the zeroth ones here. So we visualize them everywhere where the zeroth multigraded Betti number is non-zero. We put a dot, and the area of the dot is proportional to the multigraded Betti number. So for example, I should be able to hover over this guy and find out something's funny. I'm supposed to be able to hover over this guy and find out what the dimension is, and I can't for reasons I don't understand. Okay, never mind that. So similarly, yeah, the thing's acting up. That's weird. Okay, so similarly, we visualize the first multigraded Betti number with red dots, and the second one with yellow dots. And so let me try to just explain a little bit how we propose that a person might use this kind of tool in the study of this noisy data. So where I have the bar right over here, this is like looking at the RIPS filtration with no density filtration at all. So this is the version of persistent homology that people have been doing for 15 years. And we can drag this guy to the left. This is like removing points with the least dense points bit by bit, watching how the barcode changes. Right? And you see after a while we start to get this very long-lived interval. And on the right we have the persistence diagram here corresponding to that. But as I said, right, and this big blob here suggests that something is stable, but I don't know that it's stable because I can have that even when there are instabilities. So this suggests that I look at a diagonal line and see what's living across the entire blob somehow. So we do this and we see, look, there is a long-lived feature like that. So that tells me that somehow there is a significant feature across both scale and dimension. Okay, and again, these diagonal guys are stable in some sense, and we see that here. Right? Okay, so I should probably think about winding down in a minute or two. But okay, I'm not gonna have a chance to say everything I wanted to theoretically, but let me say a little bit to close. I'm just gonna talk about what this theoretical and algorithmic framework looks like. Okay, so the way that we do all of this is, in short, the way we do this interactivity stuff is that we introduce a data structure that allows us to quickly query allows us to quickly perform queries for 1D slices of the persistence module. And we call this data structure the augmented arrangement of the module, and we denote it AM like this. And this consists of two pieces of data, or two types of pieces of data. First, a line arrangement in the right half plane. In other words, something looking like this. This is a cell decomposition of the right half plane induced by a collection of lines. And then secondly, for each 2 cell in this arrangement, each top dimensional cell, I store a collection, call the cell E. I store a collection PE of pairs AB, where A is a point in R2 and B is a point in R2, which is allowed to be infinity. And we call this a barcode template. It's obtained by computing a discrete barcode, and we use it to get these barcodes of the slices on the fly. So how do we do this? Well, let lambda be the set of affine lines with finite positive slope. But it turns out there's a point line duality that maps bijectively between lambda and the right half plane. All right, so via this, I think of points in the right half plane as parameterizing lines with non-negative slope, my possible query lines. Now, I'm going to define a map, and then I'm going to be able to tell you the main mathematical idea underlying this visualization scheme. So for L, a line with finite non-negative slope or finite positive slope, we have a map push L. It sends every point in R2 to the line L, and the way that it does it is as shown in this picture. It pushes a point either to the right or above until it hits the line. And so for example, this point here, well, the line is above, it's to the right of this point, but not above, so I push to the right. For this point here, the line is above, but not to the right, so I have to push up. Okay? And so now, here's the mathematical result. It tells me for M, a 2D persistence module, L, a query line, and E, any 2-dimensional coface of the cell in my augmented arrangement data structure containing the dual of this line, the barcode of the restriction of M to this slice is equal to the collection of intervals obtained as follows. I look at every pair of points in this barcode template, and I push them onto the line, and that gives the left and right endpoints of my interval. So for example, if my barcode of ML is I1, I2, as shown in this picture, this interval here and this interval, and my barcode template looks like this, I take points A1 and B1, I push them up, and then those are the endpoints of my first interval. I look at this pair in the barcode template, I push them, and that gives me my second interval. So I can't tell you exactly how we define this arrangement or these barcode templates today, but it'll be in our paper appearing sometime this month. So I'll end there. Thank you.